What we're going to look at in simulation is we're going to start with the basis of everything, which is just a linear static stress analysis. From there, we're going to look at frequency analysis. Then we're going to look at drop test if you have a requirement for that. And then the last step will be how we can optimize our design. So we're going to look at doing a little bit of stress analysis on this plastic part. We can do many different types of study in simulation, fully integrated into SOLIDWORKS, of course. So we can do our design work, do our analysis, make design changes, go back into analysis, back and forth, very easy. These are the different types of analysis we can do. So linear static analysis, we can do frequency analysis, we can do buckling, we can do thermal if we have, heat sources and we need heat transfer, we can do that. We can do drop test, we can do fatigue, we can do full nonlinear, which is nonlinear materials. It's large displacement, large strain, time-dependent loading, a lot of different things that we can do there. Then we can also do linear dynamic, and then we can do a pressure vessel design. So we'll start with the linear static. And simulation, we see, uses a tree very similar to what we use in SOLIDWORKS. So again, not a new interface that we have to learn. So just kind of working down through the list to give you a quick overview. We have an area where we define our materials. We have an area where we define the interaction between components in an assembly. We have an area where we define the fixtures, which is how our model is held in place. We have an area where we define any of our external loads, and then we define our mesh. So just working down through the list. When we add our material, if we've defined the material in SOLIDWORKS, which we have, we've used an ABS blend from the SOLIDWORKS library, it comes across automatically into the analysis for us. The nice thing is we can define a different material for the analysis itself, which is what we're going to do here. So instead of using the generic ABS that SOLIDWORKS has, we're going to use our own. This allows us to define the mechanical properties. So elastic modulus, yield strength, Poisson's ratio, the density. So anything that we need as far as custom materials, we can create. We'll go ahead and add that to the model. Okay. Now this is just a single part, so we don't have to do any connections, but we're going to take a quick look at it. We can have virtual connectors, so we can get the effect of a spring or a bolt without actually having to model it in. Or we can define our contact sets, which are no penetration or bonded are the two main ones that we would use there. But again, we're just doing a single part, so we don't have to really worry about that right now. As far as our fixtures, the way we want our structure held in place, there's a lot of different options. So we're going to start with the simplest one first, and we'll just take a look through the list of everything else. One nice thing you'll see right away is we get a preview for the fixture type. Okay, so if we wanted a fixed geometry, we can see exactly what fixed geometry is going to do. If we wanted to use a roller slider, we can see exactly what it's going to do. So it's going to keep whatever we select locked into a plane. If we needed things to rotate, we can use a fixed hinge. Now if we go into the advanced fixtures, here's where we have a lot of freedom to really define what's going on. So if we wanted to take advantage of any symmetry in the model, we could cut it in half, and we can do that. The most generic and most powerful type of fixture we have is the use reference geometry. And what that allows us to do is control either restricting the movement in the X, Y, or Z direction, or we can actually define a movement in the X, Y, or Z direction. And that's a local X, Y, and Z direction. We're not limited to just the global X, Y, and Z. Okay? On a flat face, on a spherical face, and on a cylindrical face, those are all just variations of use reference geometry. Okay? So that allows us to define movement or restrict movement. So in our case, this plastic part attaches to the assembly by the 4 posts. So we're just going to do fixed geometry on the ends of the 4 posts. Okay? So we can add as many fixtures as we need. In our case, we only need the 1, so that's all we need there. Now, as far as adding our external loads, again, we have a lot of different options to set it up the way we need. We can add a force, we can add a torque, we can add a pressure, we can add gravity, we can have centrifugal loading, so we can't actually spin the component, but we can get the effects of it being spun, and then we can have a bearing load. Okay? So in this example, we're just going to use a simple force on one side of our plastic piece here. Now for the force, we have an option of it being normal to that selected face, or we can use reference geometry to define it. Okay? So we're actually going to use this face here, and we're going to go in the Z direction. We can flip the force around if we need to, and then we'll just add 3 pounds to that. Okay? And just like fixtures, we can have as many different loads as we need. In our case, we just need that 1 force, so that's all we're going to do. Okay? Now, as far as meshing, the nice thing is here, we can make the meshing process as automatic as we want it to be, or we have a lot of manual control as well. So we can use the slider to create a small mesh or a large mesh, or we can physically define the mesh with the size. Okay? So if we had a particular element size in mind, we could type it in. We can also use, we have several different element types available. We have solid elements, which are tetrahedral. We have shell elements, which are a 2D representation of our 3D geometry. Or we have beam elements for any structure, welded structures, structural steel, using the weldment environment in SOLIDWORKS. Okay. So we're just going to go with the default size. Go ahead and let it mesh. Now, the other nice thing is if there were certain areas in this geometry, say the posts, that we wanted to mesh a little bit smaller, we could add a mesh control on those areas, and we could make them, whatever size that we wanted. Okay? So again, a lot of freedom on how we actually set this up. So let's go ahead and remesh that just so you guys can see what it would look like with that mesh control. Okay, so there we made it a little smaller if that's what we needed. And once we get our mesh how we want it, it's as simple as running the analysis. Okay. So we can see very quickly it runs through, and we get a look at starting with stress. So, our ABS material has a yield strength of about 5,500 psi, and we're looking at a maximum stress only around 1,200. So we're not anywhere near yielding, which is nice. We can also look at displacement if we wanted to. So it looks like about 60 thousandths displacement. Now, any of these plots can then be animated if we really wanted to visualize, what's going on. And Because of the connection, you guys might not be able to see that animation really well, but it is showing how it would deform due to that load. Another nice thing that we can look at is, we've got a lot of different additional plots that we could create. A nice one is factor of safety. So basically we get a very quick go, no-go look at our assembly. So say our standard was we wanted a factor of safety of 2. Let's go ahead and show. So since our entire part is blue, that tells us that the factor of safety everywhere is at least 2. And in our case, it actually was 4 was the minimum factor of safety that we had. Okay. So now that we've got our first stress analysis done, we can look at if we wanted to do a frequency analysis. Now the nice thing is any study that we create in simulation, we don't have to start completely from scratch. We can just copy and paste stuff that we've already used. So if we wanted to, say, take the material from the static analysis, we want to take the fixtures from the static analysis, we want to take the loads from the static analysis, and we wanted to take the mesh from the static analysis. We just drag and drop, and now you can see they're all copied in to our frequency analysis. Now another nice option is if it's the same study type, meaning maybe we wanted to do another stress analysis but with different loading, we can copy the entire study. But because we're going from a static study to a frequency study, we couldn't copy everything at once. We just had to do it piece by piece. Okay? Now in this case, we've decided we don't really want to include the load. So the nice thing is, just like in SOLIDWORKS, we can suppress items. So they just temporarily go away, but we can bring them back if we wanted to. Okay, so because we copy and pasted all of that in from the static analysis, we are ready to run this. Okay. Now, don't get too alarmed by what you see there. We just need to scale the results down. Okay. So frequency analysis, let's talk a little bit about what we can get out of a frequency analysis. What we end up getting is 2 things, really. First one is what the natural frequencies, as many as we want to request, for our structure. Okay. We also get a plot of what it would look like if it actually started to vibrate. Okay. So let's look at our natural frequencies first. So in this case, we just asked for the first 5 natural frequencies. So 203 hertz, 211 hertz, 395 hertz, 406 hertz, 811 hertz. Okay? So what the usefulness of this information would be, if we had equipment running at different speeds, we could now look at, okay, I've got a motor on this, it's running at a certain RPM, what frequency does that equate to? And then I can see if that happens to line up to one of my natural frequencies. If it does, I can just then make a design change, maybe stiffen up the model, maybe I could run the motor at a different speed to shift that around. Okay, so there's a lot of good information that we get from the frequency analysis. Okay, we also, again, this animation may not come across real well, but this would be if that first natural frequency was excited, this is what the component would look like if it was vibrating. Okay. So again, that can give us good insight into where we need to stiffen it up. Where do we need to maybe add some ribs, some braces, some additional material. Now, if we needed to go a little bit further, and say, if this started to vibrate, what kind of damage is going to occur? With that, we would just move into either a full nonlinear analysis or a linear dynamic analysis, and that would actually allow us to input a harmonic load, and we could get stress and displacement values back. Okay, so this is going to tell us simply if it, at what frequencies would it vibrate at, but it's not going to tell us what damage would occur. But we can, of course, do that in other studies if that's what we need. Okay. So if this frequency range is suitable for our design, we can move on to the next step, which would be our drop test. Now the drop test is going to have a similar but slightly different interface than the other two. So the top part is the same, where we have our material. So we're going to go ahead and copy that out of our static analysis. For our mesh, we'll go ahead and we'll define that here, because we're going to go a little bit larger, just so it solves a little quicker here live. Okay. So that part of the setup is the same as what we're used to seeing. This next part is where it's a little bit different. So we don't have fixtures or loads for a drop test. What we have instead is the setup for the drop test itself. Okay. When we're setting up a drop test, we have two options. We can either drop it from a given height, or we can define a specific velocity at its impact. Okay. We're going to use the drop height option. We're going to drop it from 36 inches. And that can be measured from either the centroid of the part or the lowest point. Next thing we define is what direction is gravity. So we'll just use one of the SOLIDWORKS planes, and we want it downward. Okay. From here, we define our target, and that's what this would be hitting. That target can either just be a plane that is normal to gravity, or we could actually define a different reference plane for it to be dropped on. So say it was getting dropped onto an angled table. We would just create a plane at that angle. In our case, it's just going to be normal to gravity. The target that it's hitting can either be rigid, or we could define it as a flexible target. We're just going to leave it rigid. Okay. We could also, if we wanted, instead of just standard gravity, we could increase gravity. If we were, say, throwing it down instead of just dropping it, we could do that. And then the only thing left is we want to define how long we want to get results. So we want to look at, say, 100 microseconds after it hits the ground, and we want to get, say, 25 plots. So basically, it's going to generate results every 4 microseconds. And then we can go ahead and run this analysis. And because it's a fairly simple model with a fairly coarse mesh, it actually does solve very quickly for our drop test here. So now that this is really a time-dependent analysis, when we look at our stress results, we get a choice of those 25 plots. So if we went to plot number 1, this would show us what the stress is basically right after it hits the ground. Okay? And we could cycle through each of those, one plot at a time and see how the stress builds, or, and I'm going to exaggerate it, the scale a little bit so we can really see, what's going on. Let's go a little bit bigger than that. And we can actually animate this plot. And again, remember, it's exaggerated. Let's actually go a little less on that. Let's go about 10. That really helps us visualize, again, as it hits the ground, where we might need to stiffen up the model. We can see what the stress levels are. We can see how the stress builds in the part. That can really give us a lot of information if we have a drop test requirement. Okay. Now, the last thing we want to look at, I'm actually going to switch over to a different model. And here is going to be an example of, we've done our static analysis, we've done our frequency analysis, we've done our drop test. We've found that everything checks out plenty safe. Now maybe we want to optimize this a little bit to actually remove some material. So what we can do is use that static analysis as our basis for our optimization. So the way optimization works in simulation is we can choose several, I believe it's up to 25 different model dimensions that we want to change. We can give it the range that we want it to test over, and it will find for our different criteria what the optimal design is. So in our case, we're just going to vary the thickness of this rib here. Okay. So it started at a thickness of 200 thousandths, and we're going to let it go down to 100 thousandths. Okay? As far as what do we want to use for our criteria, we're just going to use the stress level. We want to make sure that the stress level is less than 3,500 psi. Okay? We can also monitor certain results. So even though we're not using displacement in our criteria, we can monitor it so we can see what it's doing. Okay? We can even monitor the frequency, so we can see how that might change as we change our rib cutout thickness. Okay? And then we just have to tell the software, what do we want, what is our goal? And we want to minimize our mass. Okay? So it's going to run through iterations, changing that thickness from the 200,000 that it starts at, going down to as low as 100,000. Okay? And it's going to make sure that the stress stays under 3,500 psi. Okay? And we've run through, in this particular case, because of the range that we gave it and the fact that we're only changing one model dimension, it only needed 3 iterations. So it started with our lowest value, and we can see that actually gave us a stress of 5,700, a little over 5,700. So that is above the range that we defined. Okay, so that's why that's highlighted in red. It tells us right away that's not good. Displacement was also 190 thousandths. And then we can see what the frequency was for that model dimension. Okay. Then it jumped up to the maximum, and it gave that stress value, it gave that displacement value, and that gives us a slightly different natural frequency. And then it tried one right in the middle. And you can see that happened to give us right at our limit. So we were shooting for under 3,500 psi. It's at 3,495. And we can see what the displacement ends up and what the natural frequency ends up. Okay? So now we can look at that, and it gives us our optimal design. Okay? Now we know what we would want to change our model to. Okay? Now if we wanted to, for these other, go back here, for the displacement and the frequency, if we didn't want to just monitor those items, we could actually say, well, I've decided I need a displacement less than 125 thousandths. I want my frequency to be less than, say, actually let's go greater than, say, 155 hertz. Okay. And then we can rerun our study and see how that changes things. Okay, so because we're including more constraints, it just has to check multiple things now. So what you'll see is in the background, you'll actually see the model going through those different changes. Okay, so now it's on the second run, and we'll see the results pop up. Again, highlighted red if it doesn't meet one of the criteria. Okay. So there again, the first one failed for both. All three, actually, so the stress, the displacement, and the frequency failed. Okay. So if we look at the second one, which is our thickest, it passed for stress, passed for displacement, and it passed for frequency. So worst case scenario, we're back to where we originally started. So we can see iteration 3 passed for stress, passed for displacement, and passed for frequency. Now it's just going to calculate the optimal. So you can see, as we go, if we decide to include more things, it's a very simple change and just a matter of rerunning our analysis. And in this case, it happened to be the same nominal or optimal thickness, but it could have been a different answer because we have different constraints now. So with that, that is the end of our presentation on simulation.